So our next speaker is Stan Osher, who's going to be speaking on compressed sensing, recovery, algorithms, and analysis.
Oh, as I say, usually I give the same talk independent of length of time. So 25 minutes, 6 topics. Let's see, 4 minutes a topic. So this is, as you can see, a penta chart, which I did for the Navy recently, and it's sort of appropriate because I want to cover most of these topics, if I can, or at least some of them. I was here 2 years ago, and it was an L1 orgy of stuff. And now it's more like a party in a corner or something. So here I'm back in the corner. I'm going to do lots of L1-oriented stuff. In particular, one of the things I'll do is, let's see, we will talk about applications to aerosol on mixing. I'll skip the hyperspectral stuff. I'll do a little bit of video tracking, a Retinex, and a teeny bit of learning. One of the things I'll talk about is a faster method than split Bregman. Hard to believe. But it's actually split Bregman on a dual, so if I can get to that, I'll be happy. Let me start by pressing escape and going on to a video. If I can do this right now. Okay. And here is the video, and I'll tell you a little bit about it. Make it full screen. Okay. So what we have here is a parking lot from a Delphi Army lab. Upper left, we removed 50% of the data randomly. Upper right is what would happen if you subtract sequential frames, which is not very much. Lower left is if you use a robust PCA with L1 rather than TV or tight frame, which is what we use. And lower right is the tight frame stuff. So we do a pretty good job, and you will soon see people walking through and stuff that's pretty hard to see in the original video. And we've got it down to about 3 frames a second, so we're a little bit slow, but we're getting there. And what this is basically just, unsurprisingly, minimizing the nuclear norm of one quantity plus the tight frame stuff, which I'll talk about later. L1 is sum of the tight frames of the other quantity, and subject to the constraints that what you see is what you get. And as you can see, people appear, and you sort of beat the human eye in this noisy stuff. So the goal right now is to make this faster, and apparently Larry has some good stuff to do that. Let me talk about making things faster right now with the following little new stuff. If I can make this full screen view. How do I get full screen? Okay. Okay, so split Bregman duality-based methods for solving basis pursuit problems. Let's talk about what we're doing. This is joint work with a student and a postdoc. Here's the deal. This is the usual problem that you see many, many times. As usual, it's basis pursuit. Underdetermined. There's lots of interesting algorithms, and some of which I haven't mentioned, but we'll compare against almost everything. And the idea behind Bregman, or augmented Lagrangian, or whatever you want to call it, turns out to be the following. You solve a sequence of unconstrained optimization problems. You add back the error, with what it turns out to be, and do it again, and it converges very quickly to the L1 minimum. And you can use other tricks to do the first step. So the question is, how do you solve the first problem? And, well, we'll finesse that a little bit. We'll talk about something called linearized Bregman, which looks a lot like standard iterative source thresholding, but which is different. What this does is converge to the, it's a 2-line algorithm that converges to the, what is it called again, the elastic net problem. That is, you converge to the unique solution of AX equals F when you add 1 over 2 epsilon, you regularize with X squared, 1 over 2 alpha. And you can make this is pretty fast, and you can make it a little bit faster, it stalls, by doing something called kicking. But what I want to do is make that much faster. and get rid of the alpha, both of which we will do. There's a nice paper by Wo-Tao Yin, the only paper he ever wrote without a co-author, which is what happens when you're a former graduate student. And it's a nice paper. And what he did was realize that you can use duality and get a pretty good, a pretty fast convergence. In fact, it beats his FPC. I don't know why he doesn't push it. And I will show you what he does, more or less. No, it's coming very soon. This is, okay, so I skipped a couple of pages. This is primal split Bregman. This is what you would get if you were applying so-called split Bregman or augmented Lagrangian or ADMM or whatever you want to call it. I like calling it split Bregman. To the primal problem. It's a very simple algorithm and it converges quite fast. And notice you get AA for the experts, it's AA transpose inverse, not A transpose A. That's nice because A is the short fat matrix and AA transpose therefore is easy to invert. Okay, and the resulting steps are very simple. You add back the residuals and this converges pretty fast. So instead of doing that, here's the brilliant idea, which is a simple idea. Apply split Bregman to the dual problem. So you just try every possible thing you can think of, and this is what you think of. The dual problem of the original guy was, if you remember what the original guy was, where is it? There it is, equation 2. Okay, so the dual problem looks like this. Minimize minus F transpose Y plus alpha over 2 A transpose Y, bear with me, minus this projection squared. Aha! Squared. Squared is nice because it's not 1 degree of smoother than you had before. It's 1 degree smoother than you had before. And that seems to help. The entire algorithm, after you fool around with this, is very, very familiar to people in this business. I mean, it looks like something you've done before, except the shrinkage is a little bit different. You have this shrink term squared. So when you update this thing, you solve for something, you solve for this quantity D. D is supposed to equal A transpose Y. D becomes A transpose Y eventually from the third equation, as you can see. And finally, the original guy is just alpha times the shrink of what you had. Alpha is this 1 over 2 alpha term. This is very simple, no more complicated than the original linearized Bregman algorithm. And I recommend it highly, and there'll be papers on it, I'm sure, because it's 10 times faster than anything else, just about, as far as we can see. Okay. You can also do non-negative minimization this way also, and the results beat the MATLAB code for the underdetermined case. Scouts on it, they really do. The residuals don't go down as far as the MATLAB code, but it's much faster. Okay, any questions? So there it is, one more time. It's just a bunch of shrinks, AA transpose inverse. AA transpose is a small matrix. You add back the residual, and this is, so far, the world champion, as far as I can see, for this problem in terms of speed. Moreover, we have some crazy convergence results, which I usually don't care about, but they're very easy to get. So for example, the error between the exact solution and xk is squared. The L2 error is O of alpha over k. That's an unusual result to get, right, according to my pal Goldfarb, because this is a result on the error, not on the Lagrangian or anything else. Of course, the actual convergence is much faster than that, which is typical of L1. By the way, the original primal split Bregman, or whatever you want to call it, I'm going to call it split Bregman until I die, which is not so long, actually, gives you a pretty interesting result also. It tells you that the error between the L1 norm of the exact solution and the subgradient at term k dotted with that quantity is O of 1 over k. Now think what that means. If you're doing all you have to do is look at the non-zero values of x1, that's the only ones that count here, and the sum of the, you look at the sum of the errors in the sign, in the non-zero guys, and that decays like 1 over k. And in the infinite dimensional case, that's pretty significant. That means you've really got most of the zeros right very quickly. And in fact, the reason this stuff works so well, the reason this miraculous ADMM, which has been around since 1970-something, is so perfect for this stuff is because of this L1-ish type behavior. And you can show that in somewhat more rigor, but I haven't got time to do that now. Okay, so we're going to compare with everything we could think of, and we did non-negative comparisons, and I won't bore you with, you need a microscope to see this anyway, but we beat most everything by a factor of 10 or so. The closest thing seems to be, would you believe, Wotal's dual stuff, using fancy tricks with adaptive time steps and things like that. So for example, we beat MATLAB non-negative least squares by a factor of 10 in this example, and it's pretty consistent. So that's kind of new stuff in this theoretical area. I can show you a whole bunch of results. FISTA and all that stuff does not help in this business. It seems to make things worse as far as we can see. Okay. So for example, one more time, the dual stuff beats the original by around a factor of 10 typically. And that's kind of fun. So I think we can speed up that, for example, that video we showed before, I think we can do it 10 times faster. Although that's not true because we still have to deal with the stupid SVD, so I withdraw the statement. But this part of it will be much faster anyway. So any questions about this part of it? It's a very simple algorithm. Everybody's using ADMM. I recommend switch, and you'll be happy. Okay. But it's very L1-ish. I mean, you can't do this for TV, for example. There's some special. It just turns out to be very, very simple for L1. Okay, let's do some other stuff. How am I doing time-wise? That's 3 out of 6. That's not bad. Okay. Let me show you an application of some of these things. This is L1 Retinex, which might be of interest to. Okay, can I make it bigger? Ah, full screen. Full screen, okay. Okay, this is joint work with a student, Morel, and another postdoc. Okay. And this may be new to some of you, so it's kind of fun. Color recorded by an image depends on the reflectance of the objects and the illumination conditions. We perceive constant color under varying illumination conditions. This is a famous illusion. Just take a look at it. You can see what I'm talking about. If you do that, you see what the contrast really is. So Edward Land invented the term Retinex, retina plus cortex. It's supposed to explain how the visual system perceives color. In each channel, the intensity is proportional to the surface reflectance and the illumination. We discount the illumination. Okay? So we'd like to compensate for that. So if you write I equals R times Z, take the log. You'd like to decompose and pick out E. Okay. So there's R, E, and I. Okay, and you can see what is going on there. And there's I on the right, which is the same but surprising. It doesn't look like it on the left, right? That is a bit of a surprise. So how do you compensate for that? So we've done a little bit of work on this earlier. But right now we have an L1 based theory. I love L1 in spite of the dilution in this meeting. The reflectance changes sharply. The illumination changes smoothly. Aha, sharply. Sharply means TV, something like that, right? So you use that idea. Take the gradient, and the gradient of R is sparse. Okay, the gradient of E is relatively small. This is what you get in the gradient space. So you want to recover R. There's some earlier work done. Jean-Michel Morel told me about this problem and had some nice early stuff, and he worked on it with this. And the goal is as follows. You do some kind of thresholding and get back the proper way of looking at it. So just bear with me. You're going to use this hard threshold. Okay. And you solve the equation Laplacian of R is equal to the divergence of del dot, this threshold version of the intensity, thresholded. This is kind of cute. This was done by Morel earlier. You minimize the L2 norm. And if for those of you who know fluid dynamics or whatever, differential geometry, this is decomposing a vector field into a gradient, into a gradient and a divergence-free vector field in the L2 norm. But that's L2, which is not permitted at this meeting. Okay? And it's also not very good. Okay? So instead of doing that, we have this jazzy way of doing it. We have some earlier work, which I haven't got time to go into. Here's the deal. We minimize grad R minus this threshold version. This is an L1 version of this Hodge decomposition, which is kind of cute, actually. I haven't seen it before. And it seems to be extremely appropriate for this problem. And we solve that, of course, by Bregman iteration. I'll skip all the steps, but it's easy. So this is the explanation about how we solve it, which is not important here. And here are the numerical results, and they are good. The bottom is from the L1 Retnex. The top is from the earlier version, which is pretty good, but L1 is better. And this is a little bit of a triumph. On the right, you can see you get the shadow in the right place, and you got rid of the illumination issues. Okay, so that's sort of a nice application. And here's one in medical imagery, which is what motivates some of this stuff. You have intensity homogeneity, you have additive noise, you smooth, you apply the L1 Retnex, and this is what you get. On my computer it looks good, I'm not sure about on the screen. But down below you seem to be able to see things that you couldn't see on top by getting rid of the shadows, I hope. Does it look that way? Okay, good. All right, so how much time do I have now? Oh, I have three more topics, at least. Okay. Let's do another theoretical thing in 4 minutes. Well, this is not what I expected to do, but this is fine. I'm just changing the order. This is joint work with a whole bunch of people, including Russ Warren, who lives in Chapel Hill, I think, and is here today. Let me view it. What am I doing? Yeah. Get out of here. View. Okay. Full screen. So I'll get to the applications. We're going to skip a lot of the Bregman stuff, all of it, in fact. But there's one thing I want to show. This is kind of fun. Now another example of success of these Bregman splitting, whatever you want to call them, methods. You can beat non-negative least squares like crazy also in the overdetermined case. This is much, much faster. It's a two-line, one more time, it's a two-line code, and if you use split Bregman or even or Douglas Ratchford or almost anything which is reasonable, you will beat that the third column, which is the result of the latest MATLAB stuff by quite a lot. Okay, I'll skip all that. So here's an application, which was joint work with Russ and Richard Vandenbeek. The idea is to locate and classify aerosols in the atmosphere at safe standoff ranges. And before that, before Russ heard about split Bregman, not he, but the whole community, the benighted community was doing L2, basically. So a mixture of aerosols is a difficult inverse problem. You can have lots of small changes in data can have large effects. So the solution is to use L1 type stuff. This is a little bit like a blind deconvolution problem. Russ did a fantastic job of separating it out and solving two sets of L1-oriented problems. And there they are, augmented Lagrangian. It should be called split Bregman, but these are his slides. So, okay. And you get results for the concentration, and you split them up like this. And if you compare it with Bayes, which means quadratic, which means L2, of course, you do much better. So that community is switching over right now, it would appear. And there's lots of problems in the quadratic case. Okay. There's aerosol left, dust right. Okay. And I'm going too fast, but that's life. And another thing that we have done together with us is started looking at support vector machine, would you believe? And for classification, it came up here, and then it turns out, again, skipping a million transparencies, if you know about support vector machine, you won't need this. If you don't know, I'm going too fast. But after all is said and done, the bottom line is this. There you go. One more time. Maximize or minimize X transpose AX. A is positive definite plus the L1 norm. A is non-negative. You have two projections. And support vector machine has been around for a long time. It's very hard to beat these people. It's almost impossible, but we seem to be doing pretty reasonably, according to, and I'll have verification from the guy in the audience. What makes this a little bit interesting is not only are you minimizing this typical L1-ish type thing, except the sign's wrong, but who cares? You have projections that you have to deal with. But that doesn't pose too much of a problem. You can iterate. And you can show that the limit of, well, there's many ways to do it, but one way is, I think Russ just takes P1, P2, doesn't even multiply it. But anyway, this is the algorithm, which is not too unfamiliar. And you can use proximal gradient, which also works, or Douglas Ratchford also works pretty well here, actually. And it turns out that SVM sort of beats off-the-shelf quadratic programming, which means nothing because we didn't pick the best case. But that's what this stuff is supposed to show. And maybe I'll skip some of it. But anyway, this is promising. There's something called SMO, which has been around for a while, which is tailored for this problem. And we don't do too badly compared to SMO. So maybe I'll do one more thing now. Stop with that. And I have time for one more, which is kind of fun. Okay, how do I make full screen over here? Slideshow, voila. And I got it over here too. Okay, I think. No. Over here. Which one? Yep. Higher. Higher. Ah, there we go. Left of the 73. Perfect. Slows me down anyway. Okay, so here's something which is kind of cute, which would be a curiosity, except one more time, it's extremely fast when you have sparse data. And it smells like OMP. And it looks like OMP, but it's not OMP, orthogonal matching pursuit. It's an L1 minimizer. It's joint work with these three guys from Martin Berger's group. You know, Michael Muller is quite a guy. Remember that name. He's doing a lot of interesting things. So skip all this Bregman-Schmegman stuff, but okay. These algorithms have been around forever. Linearized Bregman, which I thought I invented, is a special case of an Uzawa method from 1957. But, you know, of course, one more time, applying it to L1 and doing all these things is what makes it useful. In fact, my paper with Goldstein, may I say immodestly, was one of the most highly cited papers in the last 2 years in computer science, they tell me, Thomson Reuters. Even though it's probably not original, it's the stuff in there that's been around. Okay, here's Bregman iteration, but skip all that and get to the third equation. I need a pointer, but the equation in the middle is when you do Bregman iteration, you take the subgradient of k plus 1 minus the subgradient of k divided by lambda is equal to the right-hand side. Let lambda go to 0, and you get a PDE, which I love. The PDT is A transpose AU minus F. That's so-called inverse scale space. We're going to solve this problem by looking at that equation, not the discrete version of it. And that is going to look a little bit like orthogonal matching pursuit. However, this gives you guaranteed the L1 minimum in a nice way. And if you have sparse data, this is extremely fast. Okay. It always gives you the L1 minimum, but the speed is amazing when you have not too many non-zero quantities. I say it's the best. Let me cover that up. It's the I just showed you something else that was the best. So it was it resembles orthogonal matching pursuit, but it gives the L1 minimizer, and it's more reliable. Okay. So here we go. Here's the key idea, which is a very simple idea. And this idea is the idea of continuing in time or in some parameter is around. I read an interesting paper by Romberg and a student recently in which they did that and other people, but ours is a little bit different. We are allowing discontinuities in time. When you hit a certain t point, you jump, and you get a new solution. And at every step of the game, you change the support of what you have. So the equation to be solved involves a subgradient of L1. The subgradient is less than 1 if it is in magnitude. If a subgradient of ui is less than 1, then ui equals 0. If ui is greater than or equal to greater than 0, less than 0, then the subgradient is plus or minus 1. Very simple, right? Very special about L1. This is very L1-ish. This helps us to analyze the flow very much. You start out at ut identically 0. You're solving the equation dp dt, let me go back real fast, is equal to A transpose AU minus F. I'm pointing at the screen. Okay. So U is initially 0, which means U of t is identically 0 until you hit the first place at which T1 times A transpose F equals 1. Very easy to compute. You then, after you hit T1, all you got to do is the set of I for which P of U of T1 is equal to 1. You classify it in one way where it's minus 1, another way where it's 0, another way, and then compute U by doing a non-negative, very small non-negative least squares problem. And recover those values. Okay? You now have U of T1. That's all there is to it. Next, you repeat. You write U is equal to U of T1. U stays at U of T1. P of T moves along nice and linearly until all of a sudden something happens. It's T times something plus P of T1. And you find the first T at which P of UT is equal to 1 where it wasn't 1 before. And you do non-negative least squares again. And that's the whole deal. That's all there is to it. This gives you a sequence of very simple problems to solve, and if you have a sparse solution, this is really fast and very, very reliable and doesn't screw up like AMP does, or might. Okay? The support does not necessarily increase. When you hit one of these T1s, you might switch. You might flip the switch. In some weird cases, it does happen. But you never get something that's not in the support as you go. So you only touch the support. This is a very simple algorithm. You can't use my fancy non-negative least square stuff here. You've got to use the real non-negative least squares to get it down to 0 residual. But it's still very fast. And this is different from AMP. The support monotonically increases. And that's what AMP does. I'm not going to go into it, but... no. You mean if it's not... I've never seen... We have discontinuous jumps in U. And maybe does lasso involve the subgradient? I don't think so. Well, let's talk offline. You might be right. I don't know. We haven't seen it before. By Tib Sharani? I looked at his papers. No. I don't think so. Okay. Well, that's interesting. Okay, and you can prove that it converges to an L1 minimizing solution, and the Bregman distance diminishes like this. And for crazy results, for example, if the support of U tilde is two-dimensional, you get there in 2 iterations. Other than that, there's no precise complexity result. But you get there very quickly. Okay, and that's might be it at the moment. Okay, I can quit here, actually. Okay.
So we have time for a couple questions as we get the next speaker set up. Questions?
No.
I've got one. So you mainly were looking at you like L1 a lot, but you're mainly comparing it to L2. There was sort of James Scott's point in his talk where L1 actually corresponds to a pretty light-tailed prior. So if you have lots of coefficients in your models that are very close to zero, and then some larger ones, then L1 will tend to overshrink the signal relative to fancier penalties that would correspond to, say, heavier tail priors.
I don't know. I mean, these methods work very well for things that are homogeneous of degree 1. And that's L1-ish type stuff. I'd have to look at the other stuff. Okay.
Thanks.
Very good.
So, thank him again.